Greetings and welcome to Distilled. In the previous class, we discussed certain problems on recycle and bypass. Today, I've got a few more problems for you in bypass as well as purging. All right. So let's start with this. Example number 5. In a process for concentrating 1000 kg of freshly extracted orange juice containing 15% solids, the juice is strained, yielding 750 kg of strained juice and 250 kg of pulpy juice. So uh, strained is basically separating. Okay. Straining is basically separating the juice. All right. So the juice that contains more pulp is separated from slightly clarified juice, clear juice. All right. So even the clear juice, it would contain solids. All right. Even that would contain solids, but it won't be very concentrated in nature. All right. So it is strained and 250 kg of pulpy juice. So the strained juice is concentrated in a vacuum evaporator to give an evaporated juice of 60% solids. The 250 kg of pulpy juice is bypassed around the evaporator and mixed with the evaporated juice in a mixer to improve the flavor. The final concentrated juice contains 40% solids. All right. So let's draw a block diagram for this. So we have the evaporator. We have the evaporator. So in this evaporator, we have strained juice coming in. So let's call it S. It is 750 kg. Let's say the solids in the juice are X. This is the mass fraction of solids in the juice. All right. And let's say water leaving this evaporator is E. Okay. And then you have concentrated juice, concentrated strained juice with 20% solids. Sorry, 60% solids. Okay, so it has 60% solids. Okay, we got the strained juice from juice that contained from 1000 kg of juice, which contained 15% solids. So it got divided into, suppose here there is strainer. So here you've got strained juice and you have got pulpy juice. I'm taking the bypass stream from the down. So I have got pulpy juice here. So pulpy juice is 250 kg. And let's say solids in the pulpy juice are 5. All right. So this goes and combines with the fresh, the concentrated juice coming here in a mixer. And finally, from this, we have final juice. Let's call it P. So this P, it contains, 40% solids. Okay. So this is the problem. This is the material balance. This is your block diagram that has to be drawn. So for this problem, let's first of all make a control volume for an overall material balance. So this is my green box. So this green box, I'll draw a block diagram for this green box. So this is my green box. This is my entire system. And then I have J coming in at 1000 kg and it contains 15% solids. Then I have E over here and I have P. Rest nothing is going to be counted because all of them are system to system transfer. Okay, this one is surrounding to system transfer and these two are system to surrounding transfer. The rest are system to system transfer, so we will not count them. Okay, now for this, let's make the two equations. First, for Let's first make the equation for solid balance. So solid balance equation gives us 0.15 into 1000 gives you 0.4 into P, right? So you'll get 150 upon 0.4. That is your P. Okay, when you do the overall balance. So this is going to be a solid balance. So this is going to be 375 kg. And once you get P equals to 375 kg, then from overall material balance equation, 1000 is equal to E plus P. You will get E as 1000 minus 375, which is 625 kg. So E is going to be 625 kg over here. Okay. So you have got E and you have got P. All right. So the first part, I think we have found final concentrated juice. We have to find its mass. So that is 375 kg. Okay, it's 375 kg. All right. Then we are going to do the remaining balances. All right. So next, what we are going to do, we have to find X and Y. That is mass fraction of solids in strained juice and mass fraction of solids in pulpy juice. All right. So for the strained juice, we are going to use the evaporator. Okay, for strained juice, I'll use the evaporator. So let's make the block diagram for evaporator. So this is my evaporator. Then in this evaporator, I have strained juice, which is 750 kg. Then X is the mole mass fraction of solids. Then I have water is evaporating, which we have calculated as 625 kg. And we are having concentrated juice over here, which has solids equal to 60%. So 60% solids. All right. So using the overall material balance equation, we'll get S is equal to E plus C. So from here, we'll get C is equal to S minus E, which is 125 kg. So this is going to be 125 kg over here. Okay. So once we are done with C, then we are going to do the solid balance, of course. So solid balance gives us X into 750 is equal to 0.6 into 125. So from this, you get X is equal to 0.1. Okay, 0.1. So that means you have 10% solids over here. You have 10% solids in the strained juice. All right. Then we need this. Then we need to find the concentration of solids in the pulpy juice. All right. So for that, we are going to choose. So pulpy juice is here, right? So we can choose either this junction number 1 or we can choose junction number 2. Any one junction we can take. So I'll be taking junction number 1. So for junction number 1, when we draw the block diagram, so this is my junction number 1. This is my incoming juice, that is 1000 kg. It has 15% solids. It gets divided into strained juice, which contains 10% solids, and pulpy juice, which has mass fraction of solids as Y. So so for this, we are simply going to do our solid balance. The solid balance for this gives us 0.15 into 1000 is equal to 0.1 into 750 plus Y into 250. So that is 150 minus 75 is equal to Y into 250. Okay, 150 minus 75 is nothing but 75. So from here, you get y is equal to 0.3. Okay, you get y equals to 0.3. So that means the pulpy juice contains 30% solids. Okay, so this is your result. All right, so this was example number 5. This was again a problem on bypass. So hope you people could solve this problem. It was a simple material balance problem. Just over here, the difference, slight difference that was there, that we could also consider material balance over these two junctions, junction number 1 and junction number 2. Rest, we have done even worse, even more difficult problems on material balance, which involved so many systems, right? So this is a very easy problem in comparison to that problem. All right. So once we're done with this, then we'll come to this example. This is an example. This is a problem that came in GATE. All right. This came in GATE 1990. So this is the problem. And it's a very interesting problem. It's a very interesting problem. This problem is on purging. All right. This problem it involves purging. So this is the best example for explaining purging, explaining calculations based on purging. So it's the best example for that. It involves chemical reactions as well, although it's not very, it's not going to be used very much, but still it's chemical reactions. So yeah, we're going to use that. And then of course it has purging problem. Okay. One thing that you people are aware about purging operation is that purging is basically extension of recycle, right? So what happens in purging, suppose if this is my unit, this is my unit, this is my feed, this is my product, I am sending a part of this back as recycle, right? That is what happens. So now what happens in purging, if let's say here there are inerts, then these inerts, they come along with this, right? So what the motive is, in order to make sure that there is no accumulation of inerts over here, we get a purge stream out from the recycle stream. So it's basically an extension of recycle. So all the concepts, all the terms that we studied in recycle, per pass conversion, overall conversion, that remains same. Okay, it is basically a recycle operation with an external stream. All right, with an external stream. So don't worry about material balance and all that. It's going to be the same way as we have done for recycling. All right, just make sure that you're careful while solving this problem. So let's go with this problem. A reaction A to B takes place in a reactor. The fresh feed of A contains 0.5% inerts. So this is the block diagram. I'll not extend the block diagram anymore. So this is the fresh feed. It contains 0.5% inerts. All right. So 0.5% are inerts. That means A is 99.5%. All right. Then 60% per pass conversion of A fed to the reactor is obtained. All right. So 60% is the per pass conversion. Okay. The concentration of inerts going into the reactor at this point, say 0.1, must be held at 2%. So here we need inerts to be 2%. All right. How many moles need to be recycled per mole of total feed to the reactor at 0.1? So let's talk about that later. We'll start this problem with our basis. Okay. This is the block diagram they have given for this problem. This was given in the paper. In the block diagram, they have given A and I. A is the reactant and I is the inerts. So they have given A and I here, 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 and here. So that means over here in the product stream, there is neither A nor I, there is only B. Okay. So all the A and inerts, that is unreacted A, and all the inerts, they go here. Okay, they go directly in the recycle. All right. So from this, I get this as my recycle and this as my purge stream. All right. So these two things I have. All right. So now let's do a material balance for this particular problem. All right. I'll just remove everything, whatever. I have just written all these things to clarify the question. But now I'm removing all of it and we'll start doing the problem. So we are going to take basis. Our basis that we'll take is 100 kilomole fresh feed. Okay, 100 kilomole of fresh feed. So when we are taking 100 kilomole of fresh feed, so it contains 0.5% inerts. So that means inerts in the fresh feed are 0.5 kilomole. And A in the fresh feed is going to be the remaining. So 99.5 kilomole is A. Now, when it is mixed with the incoming recycle stream, so let's consider recycle stream to be R. Okay, the flow rate of the recycle stream to be R. All right. Now, when it is mixed with this incoming recycle stream, so you have I inerts as 2%. Inerts must be held at 2%. All right. So in that case, inert in the mixed stream, this is going to be M, right? This is going to be M. This is going to be F. This is R. This I'll take P. No, I'll take this as, let's take this as D. Anything. Okay, this is my F. Sorry, not F. This is P, purge stream. All right. So this is what my letters that I'll be using over here, right? So I inerts in the mixed stream are supposed to be 2%. So 0.02 into M. All right. So what we are going to do, we are going to do a material balance at this junction. Let's call it junction number 1. And let's call this separator. All right, let's not call it any junction. So at junction 1, we are going to do material balance. So material balance for 1. When we do that, so over here in 1, you can see you have F coming in, you have R coming in, and you have M going out. So F plus R is equal to M. This is material balance equation. F is 100. So you will get M is equal to 100 plus R. Okay. Once you get this, so you'll get IM is equal to 0.02 into 100 plus R. Okay. So this is fun thing. Okay. We'll keep this. Okay. Now let's move ahead. Now we are going to the reactor. So now 2% is inerts in M. So therefore A in the mixed stream is going to be 98%. So 0.98 into 100 plus R. I'll just write it down completely. So 98 plus 0.98 R. Okay. Now the per pass conversion is 60%. All right. Per pass conversion is 60%. So conversion, as we know, it is 1 minus A left upon A supplied or A fed. So A left, we don't know. A fed is basically AM. So it's going to be 1 minus A in the, let's call this stream as, let's call it J, anything. All right. So we have 1 minus AJ upon AM, right? So conversion they have given to be 60%. So we have, I'll write it down here. So we have 0.6 is equal to 1 minus Aj upon Am. So from here you get Aj, that is whatever the A is left. It is 0.4 into 0 into 98 plus 0.98 R. All right, this is the A that is left. Okay, so this is going to be 39.2 plus 0.392 R. That is the A left. Okay, that is the A left. Okay, so A over here is 39.2 plus 0.392 R. Now all this A, all of this A, it is going here. All of this A is going here. So therefore, all the A that is being fed to, let's call this as junction number 2, where a purge stream is being extracted. So all this A that is fed to your stream number 2, junction number 2, all A that is fed is basically Aj. All right. Out of this, A is going out for getting recycled and A is going out for purge stream. All right. But let's not get into this for now. Okay. We have found A left. Okay. We'll keep this in mind. All right. Now what we'll do, now we'll take this entire unit. Okay. From here, the entire control volume. So when we do that, when we take this entire control volume, what we have here is A, we have I. Now A is involved in chemical reactions, right? A is involved in chemical reactions. So we are not going to consider A as such. We are going to majorly talk about I over here. All right. So I here, if you remember, it was 0.5 kilomoles. We have written it, right? So I here is 0.5 kilomoles. All right. And if we draw this blue diagram that we have got for now. So in this blue diagram, we have F going in. We have the product stream. Let's call it D. That's what D we have called it. And we have the purge stream coming out from here. All right. So this is what we have. Now over here, we have inerts in this purge stream. We have inerts in the feed stream. We have no inerts over here, right? In the D stream, we don't have any. So by inert balance gives us I in feed is equal to I in the purge stream. So that is 0.5 kilomoles. All right. That is going to give me I in the purge stream. Okay. All right. Now we have done material balance here. Clear? Now we'll go to our junction number 2. Let's go to junction number 2 and see what we can get from that. So once now we go to the junction number 2. So in the junction number 2, we have let's call the stream as P1. Let's call this stream as P1. Okay. So in junction number 2, we are having P1. P1 is coming in the junction number 2. The recycle R is going here, and the purge stream is going here. So we have P1 is equal to P plus R, correct? Because see, we can do overall material balance in junctions, right? Junctions, we can do material balance because no reaction is taking place there. Even in the separator, we can do overall material balance because even here, the reaction is not taking place. But in the entire system, we cannot do overall material balance because system contains the reactor. So here the reaction takes place. So anything that involves any block diagram that involves reactor. So if you see blue block diagram also, it involves the reactor. That is why I said we cannot do the overall material balance there. So that is one. Okay, so it anything that involves the reactor where my reaction is taking place, there we can't do overall material balance. Okay, so P1 is equal to P plus R. This is the equation that we can form here. Okay, and after that, P1 would be all the A and all the inerts that have come out. So P1 would basically be A in the J stream plus inerts in the J stream. So A in the J stream we calculated it as 39.2 plus 0.392 R. So it's 39.2 plus 0.392 R. That was the A in the J stream. And we have inerts in the mixed stream, that is IM. Here we have inerts. Now these inerts, since they do not participate in the reaction, so as it is, these inerts will come here. So Ij is going to be equal to Im, right? So Ij is 0.02 M, which is 0.02 into 100 plus R. So this is 0.02 into 100 plus R. So this is basically 41.2 plus 0.412 R. All right. 41.2 plus 0.412 into R. This is your P1. Okay. Therefore, P from here you will get P as P1 minus R. Right. So that is 41.2 plus 0.412 minus 1 R. All right. So 0.412 minus 1 is minus 0.588. So this becomes 41.2 minus 0.588 R. That is going to be P1. All right. P1 in the Perth stream. This is what you're going to get in the Perth stream. All right. So once we get once we get P1, we get P. So now we also have I, inerts in the Perth stream, right? We have inerts in the Perth stream. So inerts in the Perth stream is .5 kilomolars. All right, this is what we have. Now, this purge stream is basically a portion of P1 stream, right? It is a portion of P1 stream. There is no separator at junction number 2, which is separating P1, P and recycle R, right? It is, there is no industrial separation unit that is involved here. It's just we are taking one portion of P1, right? So therefore, the composition of all the 3 streams is going to be the same, which means mole fraction of inerts in the recycle is same as mole fraction of inerts in the Perth stream. Similarly, mole fraction of A in the inert stream, in the Perth stream is same as mole fraction of A in the recycle, right? So we can calculate mole fraction of inerts easily because of course A will have R more variables, right? So difficult to solve. You can do it both ways, A mole fraction and inert mole fraction, but it is better that you use inert mole fraction, right? So mole fraction of inert in the Perth stream is equal to 0.5 upon 41.2 minus 0.588 R. Okay, keep this as your equation number 1. All right. Then let's go to the recycle stream. So when we come to the recycle stream, do we know inerts in the recycle stream? We know inerts over here. We know inerts over here. So we can do inert balance, right? So at junction 1, we have, yeah. So at junction 1, if we do inert balance, so we'll basically get inerts in feed is equal to inerts in the mixed stream plus inerts in recycle. Therefore, inerts in recycle is equal to inerts in feed stream, that is 0.5, minus inerts in the mixed stream, that is 2, uh, that is 2 minus 0.02 R, right? 2 minus 0.02 R. Oh, 1 second. This is F R M. So IF plus, wait, I'll write the equation again. In the junction number 1, if you see, you have feed coming in, recycle stream coming in, and mixed stream coming out. So inerts in feed plus inerts in recycle is equal to inerts in the merge stream. So inerts in the recycle is equal to IM minus IF, not IF minus IM, right? So IM is basically 2 plus 0.02 R and IF is 0.5. So you will get this as 1.5 plus 0.02 R. This is inerts in the recycle stream. So mole fraction of inerts. Mole fraction of inerts in recycle, in the recycle stream, is basically equal to inerts in the recycle stream, that is 1.5 plus 0.02 R plus 0.02 R upon the recycle stream, that is R. This is your equation number 2. Now you can equate equation number 1 and 2. So you'll get 0.5 upon 41.2 minus 0.588 R is equal to 1.5 plus 0.02 R whole upon R. And then you can solve for R. So when you solve for R by equating equation number 1 and equation number 2, you'll get a quadratic equation. And when you solve, right, when you solve this, you will get R is equal to 52.55. 52.55 kilo. That is going to be R. Okay. Now we have to find the moles needed to be recycled per mole of total feed to the reactor. So feed to the reactor is M, right? So M, we have 100 plus R. So M is basically 152.55 kilomole. Therefore, R by M, total moles to be recycled per mole of feed to the reactor. So that is 52.55 upon 152.55. So that is going to be equal to 0.34. That is your answer. All right. So hope you could understand this particular problem. All right. So this problem was basically an application of a variety of concepts. A lot of concepts we have applied in the same problem. All right, we have done multiple material balances. We have used stoichiometry. We have used material balance without as well as with chemical reactions. Without chemical reactions in the junction balance, separator balance, with chemical reactions in the overall balance and the reactor balance. All right, so all together we have, and then of course, the concept of purging and recycling. All right, we also use the concept, the major catch in this question, you can say, was this concept that if you're taking a portion of the stream, then the mole fraction or the composition basically of all the three, P1, R, and P, all the three streams, the mole fraction is going to be the same, right? And then we could solve. All right. Instead of using inert mole fraction here, you could also use the mole fraction of A, because the composition has to be the same. So you can use the mole fraction of A as well. All right. So if you would have used the mole fraction of A and then solved this problem, then also you would have got the result. But then it would be slightly more calculation involving, right? This problem already needs so much of calculation, and then on top of that, if you would have taken A mole fraction, then it would have involved more calculations. All right. So one more thing that you people can see from here, the inerts that we took, that they are going out of the purge stream, it is same as the inerts coming in from the fresh stream. So what will happen? The inerts that are circulating within this, they'll be constant, right? They'll be constant. It won't be that these inerts are getting accumulated. If I has come in, then I will go out, right? I will go out. Okay, so that is why purging is necessary. So this is the concept and the reason why purging is used. All right. So this marks the end of chemical process calculations. Chemical process calculations majorly involved material balance. It also involves an energy balance, but I'll cover that under thermodynamics. All right. So it majorly, we have covered material balance. So in material balance, we discussed how to construct a block diagram, how to use mass balance equations, how to form mass balance equations for various systems, and then how to solve those mass balance equations. Then we discussed unit operations, unit processes. We discussed certain basics about different chemical processes. And after that, we went on to material balance without chemical reactions. In material balance without chemical reactions, we dealt with a variety of unit operations, which involved mixing, evaporation, distillation, crystallization, absorption, extraction, right? And then we went on to material balance with chemical reactions. We discussed how to solve problems when we have material balance with chemical reactions. So there we brought stoichiometry into account. We discussed about limiting reagents and all that. After that, we went on to apply our material balance calculations to combustion. So we discussed about process of combustion and we discussed combustion related calculations. And then we finally went on to recycle, bypass, and purging and discussed problems on that. So hope material balance is clear to all of you. If you people have doubt in any process, any concept involved in material balance, please watch videos related to that particular concept again before you further switch to other subjects, because material balance forms the basis of calculations for almost all your subjects, all your chemical engineering subjects. So if you're not clear with material balance, then you would really face quite a lot of issues further. Okay, so when we are going to deal with other subjects, other complicated subjects, then at least material balance problems, material balance part should be clear. You should not get confused whenever we form material balance equations over there. Okay,